Alright, welcome back. This video will be a little bit shorter than some of our others, just because I have one quick topic I kind of want to run through on this. Okay, we've been talking about probabilities and we've been talking about conditional probabilities. Okay, well now I'm going to show you why we needed conditional probability, because what I can do is I can start to define a concept known as independence. And so that's what the nature of our video today is going to be. So independence, we're going to set it up as follows, that we have two events are independent if and only if the probability of A given B is exactly equal to the probability of A, meaning that B has no impact on the probability of A. So this could become a test to find out if two things are interacting with each other. Okay, and likewise, the probability of B given A is probability of B, and then the probability of A given B is just simply the probability of A times the probability of B. And this is the one that's really going to prove useful to us going forward. Okay, that all it is just that if I have two independent events, the probability of both events is just simply each of those multiplied together. All right, okay, now we can go through and we can do tests for multiple events. So multiple events are mutually independent if here I have A1 intersect A2 intersect A3, if that's the probability of A1 times the probability of A2 times the probability of A3. So it's this guy times this guy times this guy. All right, so these intersection operators basically become multipliers for the raw probability. So that's kind of cool. So let's try one and give you kind of a sense of what it is that independence is doing. All right, so we're going to take a crack at a scenario where students and credit cards. Back when I was in school, you'd walk across campus, and on any given day there would be 3 different credit card companies that were trying to sign students up, and they were passing out T-shirts and whatever, trying to get you hooked on establishing lines of credit with their company. You don't see that so much nowadays, but back in my day that was kind of a big deal. So this is kind of a classic problem from that era, but it does illustrate the points that we're trying to show. So all I'm going to do is I'm going to define 2 events. Event A is the event that a certain student owns a Visa card. Okay, and event B then is that the same student owns a MasterCard. Okay, and so based on some polling data, we found out that the probability of event A that a student owns a Visa was said to be 50%, 0.5. And that for a student that owns a MasterCard, the probability of that event B was 0.4. And then based on, again, on the polling data, the probability of owning both, that the student owns both, was shown to be 0.25. Okay, what we want to show is that, just as an exercise, is show that A and B are not independent to each other. Okay, and it's pretty easy. There's a couple of ways to do it. So the first thing I need to do is I need to calculate the conditional probability of A given B. So, and we know from our definition in the last video that it's the probability of the intersection of both A and B divided by the probability of B. That gets me A given B. And so we can come in, and so based off of the numbers, off of the survey data that we had, I take the 0.25 and plug it in here, and I take the 0.4 and plug it in here, and I get a number 0.625. That would be the conditional probability of A given B. All right, now to answer the question, we know that they are not independent because for them to be independent, we said that the conditional of A given B had to be equal to the numerator value. That was that first rule that we had up here, A given B and PA. Okay, and so because they are not equal to each other, we know that A and B are not dependent. What this basically saying is that the likelihood that if the student owned one credit card, they were more likely to own a second one. Okay, or in this case, they own the MasterCard. Okay, and so this came out of our definition of independence. Okay, we can also see it from our multiplication property that I just showed you, that the probability of A intersect B we showed was 0.25. Okay, well, if these are independent, then this probability should be the same thing as probability of A multiplied by probability of B. Okay, and in that case, this is what, 0.5, and this is 0.4, gives me 0.2. Those two numbers are not equal, so clearly they are dependent on each other. They are not independent. Okay, and so those are some of the things that we can kind of start to do. So it's kind of a way to kind of play with interactions of multiple events. Now, for a lot of the exercises that we're going to do in this class, we're going to take advantage of the intersection probability of A and B. That we're going to assume independence of the events a lot of times. In a lot of cases, that's usually pretty typical. All right, so let's try one. Another one a little bit more involved. Okay. All right, so what we have is we have a scenario with students taking tests. Okay, it's an exam results question. Okay, we're going to define our event AI as being the event where a student makes an error, he marks an error on question number I, okay? And the test then has 10 questions total, okay? So based off of the studies for this particular problem, the probability that a student makes an error on a particular question is 0.1, okay? And so the probability that he gets it right is 0.9. Sounds like it's setting up for a pretty good average, right? Okay, now, we are assuming that each of the events is the same. It's the same probability for all of the A's. That may or may not be true in a real setting, you know, but for this particular example, that's what we're going to say. And of course, then the A prime I is 0.9. Okay, so maybe you're asked to find what's the probability of no errors on the exam, that the student gets a perfect score. All right, so we can set this up and say that, well, we know that the probability of no errors, if we were to draw this tree, it would be 10 levels deep, and it'd be kind of crazy, but it would be, since we defined the event AI as being the event where he or she makes a mistake on it, then the probability of no errors then will have to do with the complement. And in order to have no errors on this test, he has to have the complement occur on every single one of the 10 events, right? So it has to be, you know, perfect on number 1, perfect on number 2, all the way out to perfect on number 10. And that's the only way you get no errors. All right, so if we assume that the problems are independent, meaning that problem 2 isn't based on a result from A1 and we don't get any trickle through, you know, that it's not like a multiple part problem or something like that, then we can come in and we can quickly tally up that our independence rule allows us just to take the probability of all of these events and multiply them together. This is what we said. So if this is 0.9 and I have 10 of them, then this is the same as saying 0.9 raised to the 10th power, which would be 0.3487, okay? So, but again, we made a major assumption that the problems are unrelated. Okay, all right, okay, now let's go one step further. What's the probability of at least one error? Okay, now I underlined the key word in this, okay, so at least one. So that means it could be 1 error, 2 errors, 3 errors, all the way down to 10. So if we wanted to, we could go run through the case of, well, what's the probability of 1 error? What's the probability of 2? What's the probability of 3 and stuff? And it gets kind of long. But we can also take advantage of the complement on this and say that the probability of at least 1 is the same thing as 1 minus the probability of none or no errors on this. So for this one, I could come in and say, well, that's 1 minus 0.3487. That was the number I had up here. Okay, and so it's 65% chance that the student makes at least one mistake on the test. Okay, and so all we did was just play with the complement on this guy. We've done that a couple of times now, so hopefully it's starting to become a little more clear for you as you work on it. Okay, now let's look at this in a more general sense. Okay, and this is where the power of this stuff really starts to come through. Let's define the probability of event AI as being some value of, the textbook likes to use a script P on this, as some numerical value that's the same for all of them, 0.1, 0.2, 0.7, 0.99, whatever, it doesn't matter. So then to come up with the probability of no errors from the equation that we just calculated up here is just simply 1 minus P raised to the n power. You saw this formula here, right? So if I have 10 questions, it was a 10 for n, and if my probability was 0.9 for getting it right, it was, you know, P to the n, or sorry, 1 minus P to the n power. That's all that we've done here. Okay, so now you've got a formula that I could go in and say, well, what if it's a 100-point test or a 100-question test and the probability is 0.2? Well, now you can come in and figure out and apply on one equation the probability of no errors. And you don't have to draw this tree with all the branches and then trace down all the outcomes and stuff. You now have another mechanism for being able to do some counting, and all of it comes out of this assumption of independence. Okay, the probability of at least one, which was the second part of that problem that we just showed you, then is going to be 1 minus P raised to the n. Okay, and again, n is the number of questions and P is the probability of an error, and we're assuming that we have equal likely outcomes for all of them, right? But that now becomes a very powerful approach, and in fact, this methodology is going to be crucial when we start talking about random variables and probability distributions, and this will become the basis of the start of our an expansion into our binomial theorem that we have on those. So it's kind of a cool approach. All right, so let's try another one. Okay, on this. Okay, now we have, you know, an example involving car inspections at a service station, you know, and that we're going to assume that obviously that each inspection is independent of the one before it. Okay, and so we're going to define our event AI as being a car passes inspection on visit I. So the probability of it passing inspection is 0.7 for us on that. Okay, what we want to find then is the probability of all of the next 3 will pass the inspection. Okay, so we're looking for the event, the probability of A1 and A2 and A3, the intersection of those. That's the way we write the event in terms of our sets. Okay, and so we know that if they are independent, then it's A1 times A2 times A3. And that's what we've done. So 0.7 times 0.7 times 0.7, that's also 0.7 cubed would be 0.343. Okay, we could go in and say the probability that at least one of the next 3 fails. Okay, well, we could do that a couple of different ways. We could do the complement like we showed on the last one, or we could come in and say, well, that's the probability that at least one fails would be the probability that 1 fails or 2 fails or 3 fails. Notice that there's no 0 on that. So this is another way to do it without doing the complement. And again, for large numbers of inspections, I would keep adding terms over here on the right of this thing. It becomes a little unwieldy, but for 1, 2, or 3, it's not too horrible as we start to kind of work on that. All right, so what I've done, just to kind of as an exercise, is I've graphed out the tree diagram for this whole thing. And so you can start to see kind of the events. And so just like we've done before, my sample space S is here. Here's event 1 passes, event 1 fails. Event 2 passes, event 2 fails, event 2 passes, event 2 fails, and so on. And so you can see each one of these has 2 options. This is an A3 passes, A3 fails, A3 passes, A3 fails, and so on down there. And so the events that happen on our tree as they come out of here, the first one that comes up this first branch is A1 intersect A2 intersect A3. This is actually one of the ones that we were looking for earlier. But in this scenario, we had none that failed. Okay, if I come down to this next branch, I've now gone pass, pass, fail, so there was 1 fail. And then, coming in out of this one, it's pass, fail, pass, 1 fail. Okay, and then pass, fail, fail is 2, and so forth and so on. And so what I've done is I've tallied up all of the events, and you can kind of read through, you can pause the video and read through these if you want to see what they are. But it's just basically defining the paths that are going through to get me to a specific outcome. And so 1s and 2s and 3s, and then of course my 0 happening on here. Okay, and so now the interesting thing that happens when I add all those up, and I go and find the probabilities of all of these AIs that are in here, the probability of this event and this one and this one, and when I sum all of those together, the probability of those events is 1.0. Okay, and so that's our total probability requirement from back on like day 2, involving our axioms. Okay, so that's a way to kind of visualize what we can do. So what I could do is I could actually start saying, well, if I want the 1 events, well then all I would have to do is come up with this guy is 1, this guy is 1, and this guy is 1. So find the probability of these 3 events, add them together, and that's the probability that I get exactly 1 that fails. Now, this particular question obviously was looking for at least 1. So again, that keyword at least, that we had here, that's at least. So that's kind of the way that we can approach it using our tree diagram. Again, I do this just to kind of illustrate, how you can kind of build your way up to the process doing the stuff that we know. All right, so let's take a look at something that happens with and we kind of discussed this a little bit already, an example. What's the probability that exactly 1 of the next 3? So on our table, as we talked about, it was these 3 events. A1 intersect A2, not A3, A1, not A2, A3, and not A1, but A2 and A3. Those are the 3 events that would define the exactly 1 case. So all I've done is I've come in and said, well, the exactly 1 then is the probability of those 3 events. And so I've written them here. Okay, and so each one of these, if they're all independent, I can tally the first one as being 0.7. That's the first one passes. Okay, and then the next 2 have to fail. That's exactly 1. Okay, so 0.3 squared. And likewise, this one, 0.7, 0.3 squared. And this one, 0.7 and 0.3 squared. What do you notice about all 3 of those terms? They're 3 different events, but they're the exact same formula on there. So that's kind of cool. So even though I had 3 events, we can kind of rewrite this as being 3 times 0.7, 0.3 quantity squared. And I can do the math, 0.181. But let's take this thing and let's be a little bit more general about our approach on this. Okay, and so let's take a look that, let's define a couple of variables in this. That in order to establish this equation, okay, I can define K as the number of successes that I'm searching for. And N is the number of trials. So I was looking for 1 success and I have 3 trials. And then we'll define P as the probability of success. Well, it turns out if you look at this was a success case and this was my fail case. Okay, that I can write a general equation that defines a number k number of successes in n trials as simply being, if I look at the parts of this thing, I can raise p to the k. So that's the probability of success raised to 1 success. And so that's what we saw here, 0.7, and that was a 1 hanging out right there. Okay, multiplied by then the probability of failure, or the complement of p, 1 minus p. Okay, and then the number that it's raised to then, if you notice I had a 2 here, so this is going to be n minus k, right? So if it's not a success, it has to be a failure. Those are those points. The only other piece that's left is figuring out, how do I get this 3? Well, it turns out, and when we get to binomial, I'll derive this out a little bit better for us, but it turns out that that first number that's right here on this is actually a combination calculation of the number of ways that I can pull 1 out of 3. Okay, and for that, there's only one way to do that. Or sorry, there's 3 ways to do that, right? This guy, 3 to 1 is equal to 3. Okay, and so that's the combination. And this is probably one of the most powerful formulas in all of probability, because this is known as the binomial probability distribution equation. It works for any k less than or equal to n. So even though I set it up off of 1 success in 3 trials because I could write all these out, now I have the possibility of being able to go and say, well, what if I have 10,000 trials and I want 512 successes? One equation will get you that number without having to draw a tree or anything. So it's another counting mechanism for probability kind of at work for us, using those counting principles that we talked about. If you're struggling with the combination equation, go take a look at the video that we have for that, and hopefully it'll help clarify some things for you. But it's very, very cool the way that we can do it. And this formula, we will hit this one really hard probably in the next couple of videos. Maybe not the next one, but I think the one after that is where we really get into the depth on the binomial and can do some awesome things with that. Okay, so all right, so for our last example, what we want to do is we want to look at the probability that if at least one passes, they all will pass. Okay, now you kind of look at the wording of this question. You might go, well, what kind of question is this? What is it asking us to find? And so I'll give you a little hint. We're going to take this if, and I'm going to replace the word if with a given on this. Okay, and if I do that, then it's a probability that given at least one passes, they all will pass. This is a conditional probability problem. Okay, so if we look at this, we can come in, and the way that we would solve this is asking us to then find the probability that all pass given that at least one passes. So what I've done is I've set up this as event A, I've set up this as event B, and I've gone back to our conditional probability definition. Okay, so it's the probability of A given B is equal to the probability of A intersect B over the probability of B. Now, this is where, we can't blindly use our formula, but we have to kind of think about what it's saying. This top term is the probability of both A and B happening. Okay, and so if you look at what's happened on this, clearly if they all pass, at least one of them had to pass. Okay, so what this is on a Venn diagram, if you look at this, is if that's my event A here, inside that circle, event B is living inside of event B, right? Because in order to have all 3 pass, B1 has to pass. So what we do is we modify this formula. So again, this is one of those reasons I say, don't memorize formulas blindly. You have to understand what it's saying and be able to kind of reason your way through, right? So that's why I can make this substitution that probability of A intersect B is just the probability of A. And so then the probability of this conditional is the probability of A divided by the probability of B. All right, so if they're all independent, which is what we're assuming obviously in the case of this first one. All right, so the probability of all passing then is 0.7 raised to the 3rd power, and then the probability that at least one passes is 1 minus the complement of all fails. Okay, we've done that a couple of times in this video already. So 1 minus 0.3 quantity cubed, and when I do the math, I can solve this question as being 0.353. Congratulations, you just did one of the hardest conditional probability problems in the chapter, and all because you were able to understand and be able to correlate this thing back to an expression that you could then write formulas for. So with that, I will go ahead and stop our video for now. I hope it's made sense, hasn't been too cryptic. As always, if you leave us a comment down below, we'd greatly appreciate it. Let us know what we can do to improve your experience. And if you like the video, please toss us a like, and as always, subscribe to the channel. And with that, I will bid you all a fond farewell. Have a great evening. Happy engineering.